Oh, hi everyone. My name is Li-Heng Chen, and I'm a PhD student from UT Austin. And today I'm gonna talk about how we perceptually optimize for deep image compression model. And actually, this topic is quite similar to what iSize just presented, but I think their work are like alien technology, and my work is like PhD student technology. So okay, so I believe in this morning, George has already thoroughly introduced the history and state of the art of this kind of deep image compression. And in fact, our work is built up on top of Johanna Ballet's 2017 model, which is not a state of the art. So you can find everything about it in the link that I provide on the slide. So now I'm gonna briefly introduce it. So in the slide, you can see there's an X, which denotes the pristine image, and X hat is the decoded image. And so they use a 3-layer of convolutional neural network to serve as a nonlinear transformation. And they use a GDN function instead of ReLU, which George has already mentioned this morning. And so later on, we got Y, which is you can think of it as a transform coefficient or latent representation. And they use, what's special here is that they use a uniform noise as a quantizer, because the conventional ladder-shaped quantizer is not differentiable. So they use this as a proxy of the quantization in training, and they have a arithmetic coding, and to optimize this neural network, they define a rate loss, which is just a negative entropy, and there's also a distortion term, which is just a L2 norm between the reconstructed frame and the pristine image. So this is actually an emerging research field, but most of the people are working toward gaining the RD performance of PSNR. And I'm not a very competitive person, so I decided to go on the other way. So in fact, there are many other perceptual quality models out there, such as structural similarity or VMAF developed by Netflix. And so we decided to investigate into the potential of optimizing toward this kind of perceptual matrix. And actually, someone has already used structural similarity as their objective function to optimize this kind of framework. But actually, some much more complex models might be not differentiable or being too complex to integrate it into this kind of pipeline. So we want to solve this problem. And a first intuition to solve this problem is using a pre-trained network as a proxy of a complex perceptual matrix such as VMAF. So here, basically, I developed a very simple convolutional neural network, and given a pristine image and a distorted image, I can calculate their VMAP score, so I can learn a proxy of VMAP score. Actually, I can learn a neural network to predict a VMAP score here. And on the right-hand side is the network structure, which is quite simple. So after I learned this, I just plug in this prox IQA network with the BLS model, which is the compression network, which I just introduced. And as its loss function, this as a distortion term. But actually, this intuitive method has some problems. The first one is that when we try to train this prox IQA network, we can gather some available database, and because and because they are pristine images and distorted images, so we can calculate the VMAP score of these patches and to train the model. But actually, from the figures that I shown in this slide, they look quite different from what I actually got from the deep compression network. So these training set might not be optimal to learn the ProxIQA network. And the second problem is quite interesting. So when I first finished building this pipeline, and I input the source image, which is figure A in the slide, and then what I got is figure B. So it looks quite dirty and strange. So at first I thought it was a bug, and so I start investigated, and so I measure the VMAP proxy, which is the score produced by the neural network, and its actual VMAP score, which should be very low because, as you can see, it's not an image. Yeah, so this is what I got at first. So a way to explain this phenomenon is that the compression network produced something very strange to fraud the ProxIQA network, because this you will never get this kind of image within your training set when you want to learn the proxy of VMAP. Yeah, so you cannot expect what the neural network would extrapolate when you feed this kind of data into it. Yeah, so in this slide I provide some numerical examples. So there are two curves. The orange one is the score produced by VMAP proxy, which is the neural network I built up. And then the blue curve is the true VMAP score. And the x-axis is the training step in log scale. So you can see that these two scores are, on the left-hand side, when I use a pre-trained model, they're quite diverging, meaning that my VMAP proxy network is not predicting very consistent with VMAP score. So I come up a solution to this problem, and the figure B is the results. So you can see they are quite consistent. So now I'm gonna introduce how I solve this problem. So on the left-hand side, actually it is the same with what I just presented, where I combine a ProxIQA network, which is a proxy of VMAP and a deep compression network, and I want to use it as a loss function. So to optimize for a deep compression network, its parameters need to be trainable. But for the ProxIQA network, I need to fix its parameters. And after I update for the left-hand side, I can get X and X hat, which are the pristine patch and reconstructed patch. And I can calculate their VMAP score using their true VMAP score, which I denoted as M of X and X hat. So I use these data to update the ProxIQA network, which is on the right-hand side. So you can, and then after that, I'll update the deep neural network and update ProxIQA network. So this is kind of an alternating learning framework. So you can imagine that the deep compression network is a chef, and it takes some ingredients, which is the pristine image as its input, and it produces a food. So the ProxIQA network is kind of a customer, but when ProxIQA network eats the food, and there's a mysterious song telling him that whether this food is delicious or not. And the mysterious song is the true VMAP score that we calculated. Yeah, so this is the loss function that I use to optimize for this framework. So you can see there are some loss functions that I denoted as black fonts, So like rate loss and pixel loss. These functions are what Johanna Balais originally used in his framework. And the blue functions are what I added into this framework. So basically, I add an LP term, which is VMAF max means is 100. It's the maximum value of the dynamic range of VMAF. And the VMAF prox is the neural network given an X and X hat. So this is the prox IQA loss. So I added into the loss for the RD cost for optimizing the deep compression network. And in the stage of optimizing prox IQA network, I simply minimize the L2 norm between VMAF and VMAF prox. Yeah. So here are some numerical results. So these numbers are BD rate. So negative means we save bits by doing this. And BOS MSE is Johanna Balais 2017 model optimized for mean square error, and we use it as an anchor to measure BD rate. And as you can see, when we optimize BOS model for using VMAF proxy, and we can get quite significant BD rate reduction on VMAF. And what interests me is that actually you can see SSIM and MSSIM and VIV also got a bitrate reduction, which somehow indicates that VMAF is quite a promising perceptual metric. And as you can see, PSNR drop, the performance of PSNR BD rate kind of dropped because this is normal, because the original framework optimized for mean square error. So it should get the best PSNR result. And we also tried to optimize for SSIM. This is just a demonstration of the generality of this framework. But when we apply this on BOS model, the performance is still not as good as HEVC Intra and JPEG 2000. Yeah, because BOS model is not the latest one. And actually, we also try to put this framework on the hyper prior model recently, and we also see a similar coding again. So here are some perceptual results. So, and on the left is RD curve. So you can see that, and this one demos the low bitrate scenario. So you can see that VMAF proxy optimization is better than the baseline, which is the mean square error optimization. And you can compare baseline and VMAF proxy. You can see the numbers are much more clear. And this one is demonstrating the high bitrate region, but the PSNR difference is not quite significant when you look at perceptually. So we can demonstrate that by keeping a similar quality, we spend less bits in this case. Yeah, and okay, so it's about the end of my presentation. So these are some collaborators of this work. So if you look closely on their photos, they have a better looking than me. So I decided to compress them a little bit so that they have a similar perceptual quality than my face. Okay, this is the end of my presentation.
Any questions?
Don't ask me.
You've obviously solved it. Nobody can think of anything to ask.
Yeah.
Fantastic. Thank you.